Thank you, everyone, for attending today. My name is Mike McGurk. I'm, as of a week ago, an associate professor at Colorado School of Mines. We had a very good month. We also got our third early career award. We got the NASA Early Career Award this month, so it's been a good month, I would say. I'm very grateful for the invitation. In the past, I guess, 5 years, I've developed a really great relationship with both Eric and Pierre. They've been incredibly supportive of our research program. And it's incredibly nice to be back in Northwestern, where I first got exposed to diffraction, specifically working with the amazing Charlotte. We have a long-running professional and relationship and friendship that's been amazing. We still work together, so it's been really wonderful. I just want to really briefly introduce what we're talking about, specifically the applications of these techniques to porous frameworks. But before I do that, I want to kind of tell you about where I'm coming from. So if you've never heard of Colorado School of Mines, I don't blame you. It's a weird name, I understand. But we're based in beautiful Golden, Colorado. This is just 10 miles west of downtown Denver. So these two mesas, right on the other side of the mesas is downtown Denver. And then my office is right here, looking out on the foothills. It's a really beautiful place to work, and that is the famous Coors Brewery. So another really important thing about working at mines is that we're just 2 miles from the National Renewable Energy Lab. It's called NREL for now, depending on how the government goes over the next 6 months. But a lot of us have joint appointments at the National Lab. We're just on the other side of the mesa here. Another amazing thing about being here is that we're an hour from all the major ski mountains. This is actually from this weekend. We spent the last 3 days at Breck, me and my family. These are my twin 5-year-olds, Jack and Malia, and my beautiful wife, Lindsay, and we had a nice weekend skiing. So this is my ad for Colorado and Colorado School of Mines. Anyways, so let's get into the science. And so what I want to do is tell you kind of abbreviated two stories. One, our work looking at flexible metal organic frameworks, and two, our work looking at non-covalent interactions to build new types of permanently porous materials. So first, let's talk about flexible systems. And so I do want to kind of motivate what we're talking about, but also show a lot of structures. And so it's going to be a kind of a combination of narrative and structures today. So our motivation for the work that we do with flexible systems is really trying to attack this kind of mushy middle of the infrastructure of gas production, storage, delivery, and use. Where if you think about something like the hydrogen economy, is that once you theoretically make it through electrolysis, you need to store it, you need to move it, and then deliver, store again. But when you do this, especially with gases like hydrogen, you either need to pressurize out to around 700 bar or cool down to 20K, depending on the situation. That's a lot of energy. That's a lot of money. And so, of course, we're not the people to come up with this idea, but basically, can we make some sort of sponge for these systems in order to be able to densify these gases under more mild conditions? And of course, especially being here at Northwestern, I remember when Omar was a research professor. All right, don't let him get too big of a head around here. Now he's department head. I know he's not here today, so I can talk crap about him. No, I love Omar dearly. But I would say that in this whole field of porous frameworks is that there's a kind of continuous, I would say, problem in many ways is how rigid materials interact with gases like hydrogen. Is that you're going to get this kind of type 1 linear isotherm, a diminishing return as a function of pressure. And this becomes a concern when you think about a process where you have gas being stored at high pressure, but then when you want to deliver that gas, there's going to be a minimal threshold that is basically the concentration of gas that you can deliver that is still able to drive and function in your process. And because of the shape is that you're going to get basically this gas down here stuck in your system. And so the actual usable or deliverable capacity in your system is much less than the total capacity. And so what we've been working on is basically trying to find ways that you have a fundamentally different response of absorption with pressure, where you have basically some minimal amount of absorption occurring until some threshold, steep absorption followed by a plateau. And the reason why we'd want that is because when we have our adsorption and then our desorption, is that all of a sudden the amount of gas that is actually you can actually put into the system is very similar to the amount of gas you can get back out of the system. So you're trying to obviate kind of this core inefficiency in the system. And so the reason why I tell you about this is because we've been doing these with metal organic frameworks. Specifically, most of the work that we've been doing is based on this system called CDF13. So CDF13 is actually a material I discovered when I was a postdoc, and it's just been a kind of a wealth of a platform in order to kind of study and be able to build out our understanding and its utility. And so very simply is that we have this benzimidazolate-based linker with a cadmium-2 salt, and we make this sodalite topology. And so because we have these relatively weak cadmium-nitrogen bonds that are kind of the coordination skeleton in the system, we were able to get really beautiful single crystals. And so these structures that I'm showing here, or this is all one structure, comes from single crystal originally. And we have all these different points of view because this structure is kind of hard to look at, is that we have these repeating cages that I've shown again here. Then in these cages, we have these individual faces. But really what we have here are these rings of coordination with those benzimidazolate linkers kind of sitting at around a 45-degree angle. And so, like I said, the structure would be kind of hard to look at because it is relatively low symmetry, and you have a lot of these kind of dangling organic systems. And so that combined with kind of the visual density, we like to do a lot of different representations of the system. And so the reason why, oh, and also we like to play games where we take the linkers out to kind of correlate the linkers with the coordination lattice itself. But the reason why we're interested in this material and why we continue to study it is because it gives really beautiful step-shaped isotherms. So that type 5 or step-shaped isotherm I showed before, where in the original work we were working with this, we were looking at methane, and we can see that we don't have that type 1. What we have is a very flat pre-step region, and then there's some threshold, and then we see a step. And this was behaving really beautifully for methane, but when we went to study it for hydrogen, we could see that even at 77 K out to around 100 bar, we weren't seeing this response. And so at this point, you kind of have two questions, right? If this is the, if these are the structures before, we have this knowledge here. The two questions are, why do we have this response here? And why is this not opening for hydrogen, or is not responding? I kind of give it away there with hydrogen. And so this was actually now we're the first time where we started working with Pierre. And we actually got this beautiful structure from single crystal kind of by accident. So I don't know if you remember what happened here, but we sent him a sample where we had made this with DMF in the pores, and we had slowly exchanged the DMF that was in the pores of the framework for chloroform. And we knew that there was still some chloroform there, but we really wanted a structure where there was nothing in there. Pierre took the crystal, put it in the oil, and then mounted it and got a crystal where it was completely solvent-free. Turned out the chloroform had kind of like diffused out of the crystal into the oil, and we got a completely solvent-free crystal that really changed a lot of the trajectory of our research. So that was a beautiful accident. And so what we see is that when we make this system, we have kind of this open pore phase. But then when we remove all the solvent out of the system basically relaxes on itself. So you get a distortion of the coordination lattice, but it retains all the connectivity. But really what you see here is that those linkers are rotating from being kind of open to being very clearly CH pi sacked. And so you have basically a gating phenomenon that's going on in these pores. And so when this system shows that type of absorption, what you're basically doing is going from this state. There's some energy threshold that has to be overcome by the de facto concentration of the gas, and it goes to this more open state. We've done a lot of in situ studies looking at this more specifically, but I just kind of have to summarize that here. But by using the crystallography, what we were able to do was basically infer what was the Velcro that closed the system. And what we needed to do, because hydrogen couldn't open it, we needed to weaken the Velcro. And so we could see that there was pretty clearly CH pi stacking or CH pi interactions going on here. And so what we decided to do was basically take a second organic linker and more or less synthetically dope it into the lattice. And what we're really focused on are groups where this would more or less invert the electrostatic potential on those organic linkers and weaken the Velcro. And so skipping a ton of work that was done, specifically by Origid in my group, is that what he was able to find is that by doping in this fluorinated linker, where you're inverting the electrostatic potential of those arene rings from going CH to CF, is that you basically weaken and lower the energy barrier for the phase change. And this became apparent when we were using propane as a low pressure, high throughput probe with the original system. Now this doped system, you can see that the step onset is at an appreciably lower pressure over here. And that told us that we could go back and do the hydrogen measurements again, because those are hard to do, those high pressure hydrogen measurements. And so again, so here's the original system. And now just about 7% of another linker doped into that lattice, we can see that the pressure response completely changes. And so with that, we could also then really hone in on the fact that, going back to that original motivation, is that we can see is that if we do these pressure swing situations, is that so much of that total capacity is now being captured in that usable capacity. But the real story here is relevant to what we're talking about today, is that we had something where we are taking a core measurable, like a gas absorption isotherm, and seeing something extremely peculiar. And then going back and doing the crystallography, we could basically build out an intuitive mechanism for how the system is working and then modify its behavior to do what we wanted it to do. And so crystallography was really at the core of being able to do this with any level of intuition. And so at this point, I like to joke that the Department of Energy hates cadmium because they told us we could not work with cadmium-based systems anymore if they were to keep giving us money. And so what we've been trying to do, and I'll just talk about this really briefly, is move to systems that have much more quote unquote innocuous metals and try to push those capacities even higher. And so we've gone on a journey with a lot of different systems, but we've actually started to get really interested in a very old system. And this is the MIL-53 with aluminum as the inorganic node. And it turns out, lucky for us, that is, although the MIL-53 family is one of the originally studied flexible frameworks, it's actually very, very poorly understood because people didn't do the crystallography. And I think that's really what we're learning, is that people are making a lot of very loose assumptions about the behavior of the system without actually doing the rigorous crystallography. And so that's what we're trying to do now and solve and ultimately correct a lot of information that's out there on this very famous system. The reason why is because we do see this behavior, very high capacities for hydrogen 77K. This is what people have proposed was going on in this system. Just if you go back and look at these papers, it's infuriating. They'll literally just like see this and say, this is what's down here, this is what's down here, with no crystallography. And so what we've been doing is leveraging micro-ED. And the reason why micro-ED has been so critical to this is because these are aluminum oxo-coordination. These are very strong bond coordination interactions. And if you've ever worked with metal organic frameworks before, you know that the stronger the interactions, probably the smaller the crystallites you're going to get. And so these are very fine powders, garbage for single crystal, perfect for micro-AD. And so with Chris, actually here at Northwestern, we've been sending samples. And so we've been able to get these beautiful samples with resolution that's never been seen with these very, very famous materials for a long time, both with the baseline system and a couple derivatives that we've been working on that are showing some extremely peculiar behavior that I don't have time to get into. But we're able to see these really beautiful structures in a way that hasn't been done in this field before. So I think the work that we're going to be doing with this is going to be really kind of an example of how with the analytical technology moving forward and the analytical capabilities moving forward, we're going to be able to solve a lot of questions that have been outstanding in the field for quite a while. Okay, so I want to then transition to talking about our work looking at chalcogen bonded organic frameworks. So this is a class of materials that my group has actually invented in crystallography. Both single crystal, all three, single crystal powder and micro-ED have been a critical part of this journey. And so the large scale motivation for what we're doing is much more fundamental. This fundamental motivation of thinking about what makes a material. Materials intrinsically have some unit of matter that's repeated in space, but then there's connectivity. That's the core difference, is that we have matter connected in space. And the properties of those materials are intrinsically linked to not only that unit of matter that's repeated, but how it's connected. And I think the field of porous frameworks really beautifully encapsulates that dependence on material properties to connectivity, where we have things like metal organic frameworks, covalent organic frameworks, and hydrogen bonded frameworks, where we get very similar topologies, very similar organic moieties incorporated into those systems, but their material properties are intractably different because of how they're connected in space. And so very, very open-ended question. If we find some new mode of connectivity to build materials out, what's going to be the properties? All right, so very simple, very open-ended question. And so I do need to show you what I'm talking about. I do have to introduce a little bit of orbitals here in terms of talking about what these interactions are. So what we're focused on is a broad class of non-covalent bonding called sigma hole bonding. Sigma hole bonding is an overarching term for things like halogen bonding, chalcogen bonding, pnictogen bonding, tetral bonding, main group non-covalent interactions. The simplest way to think about this is an analogy with a hydrogen bond. So the hydrogen bond is fundamentally a weakly electronegative element polarized by a covalent bond with an electron withdrawing group, leading to polarization of the electrostatic surface potential, allowing for electrostatic interactions with a loose base. So if we have a main group element that is also weakly electronegative and polarized, because of the lone pairs and because of the contribution of a p orbital to the antibonding orbital, not just the 1s, is that we get that same polarization in the presence of a positive surface potential, but it's much more defined. It's much more of a hole as opposed to a whole surface. And so what we have here is a primarily electrostatic non-covalent interaction with a main group element. And so I do like to point this out is that all the chemists in the room, we do a terrible job of talking about electronegativity. I like to say that professors lie to students about electronegativity because we basically point our laser pointer here and then point it up here and say that's the trend. And I don't know if you can see, but there's a lot more going on. One of those things that's going on is that electronegativity plummets off that first row. And by the time you get to tellurium, an element I'm going to talk about here in a minute, you can see that those values are the same as hydrogen. All right. And so these types of interactions are fundamentally conceptually similar to a hydrogen bond, but there are core differences that we've really been studying. One of those differences is that these are more directional than a hydrogen bond. We're told hydrogen bonds are kind of the preeminent non-covalent interaction for directionality. These are even more directional. So theoretically, they're very poised for building crystalline materials. And that's because of the focus of that sigma hole relative to that more hemispherical surface potential in the proton. We also have diversity. Protons are protons, hydrogens are hydrogens. But what we have here are 4 different groups of the table, 3 of which have been well explored. One's a little bit more theoretical. So in each one of those cases, we have theoretically 1 sigma hole for every covalent bond. And so a halogen, like an iodine, you have 1 covalent bond, 1 sigma hole. A chalcogen, like tellurium, you can get 2. Pnictogens, you can actually get 3, and that's been experimentally shown as well. So we have diversity, we have elemental diversity, we have valence diversity, and we have this directionality. And so when we got into the field, and when I started my group, we were really focused on trying to take the field from kind of this niche crystal engineering, let's just see what happens type of approach to asking the question, can we build functional materials through these interactions on purpose? And so because of my postdoc, I was really focused on porous frameworks. And so we asked the question, can we build permanently porous materials through these interactions? All right. And so although halogen bonding was definitely the most well understood interaction at the time, because there's only 1 of these holes, we decided to go next door to the chalcogens where there's 2, theoretically forming more interactions per unit volume, creating more architectural soundness. And so just for the kind of continue this description is that if we have a chalcogen now, so selenium and tellurium as well talk about primarily, you have 2 electron withdrawing groups, and you can theoretically be able to form 2 of these interactions on a single atom. Okay, so the question became, can we build materials out of chalcogen bonding specifically? All right, so I have a point in space. Now I need to get to a 3-dimensional system. First thing I need is a molecule. And the system that we decided to work on were these chalcogen diazoles that because of the symmetry and planarity is that these can dimerize and also theoretically form 1-dimensional polymers, or non-covalent polymers, if you will. What element do I use? If I go from sulfur to selenium to tellurium, the dimerization strength gets basically exponentially stronger. And it turns out that this strength, if you do the same calculation with basically urea dimerizing, this is stronger than urea dimerizing through a hydrogen bond. So these are very strong non-covalent interactions. And so we set out on this molecule here. I don't have time to really explain why, but we have this rigid tryptosine core with these chalcogen diazolyl moieties on there. We could do ESP maps using DFT, and we can see that if we go from sulfur to selenium to tellurium, this blue spot is getting darker and darker. That again is our sigma hole. All right. So we wanted to work with tellurium. If anyone's ever worked with tellurium in here, you know that it's not easy. So what we first started on selenium, And then I'll show real quickly gone on a journey to tellurium. This is the actually not the only organic chemistry I'll show, but I won't show too much organic chemistry, I promise. But if you want to do a super fun, super dangerous reaction, do a hexanitration. This is the first reaction ever done in my lab. The laughter comes from clearly the organic chemists. Super dangerous reaction. Head to toe suit. Okay, but this is our molecule. Trip 3 says. Okay, we're back to crystal structures, I promise. Okay, so when we took this molecule, what we wanted was to form one of those honeycomb type structures that I showed at the beginning of this section, where the only thing connecting the molecules in space were interactions between selenium and nitrogen non-covalently. Not even close, all right? So when we crystallize this out of chloroform, these are all single crystal structures from single crystal, is that I have my 3 views here, so kind of macro, kind of more local, and then the spaghetti from mercury, all right? I just like that image. There's no real information out of it. But what we can see here, and again, this is, and, one thing I like to always say to students is that there's no such thing as a failed single crystal structure. Single crystal structures, even if they're not what you wanted, have so much information in them. And so I think this is one of those examples where we saw this. It wasn't anything close to what we wanted, but it was very clear that was causing this kind of densification of the system or interactions with the diffuse pi clouds of our system. And so we said, if we want to get to a less dense system and allow those calculation bonds to take over, we need to disrupt those pi-based interactions. You have to take information from structures, even if you don't think it's anything that you wanted. I think that's so important. And so we went and actually took these chloroaromatic solvents that are well known to break up pi-based interactions and started growing crystals out of those. And we went on this journey where we were able to get all these different structures, basically increasing the effective porosity of the system and decreasing the density, while also increasing the amount of those contacts between selenium and nitrogen. And eventually, we were able to get to exactly the structure that we wanted. We have this low density structure where there's 2 nanometer pores. There is the sorted solvent in this structure, but the only contacts between those molecules in space are these selenium-nitrogen interactions. We got this structure basically 10 days into the pandemic. And I was sitting, my twins were 6 months old, and I was in the lobby of a Target while my wife was panic buying diapers, and get the structure on my phone, and I start screaming. And everyone's like looking at this like crazy guy with kids screaming in the lobby of Target during a pandemic. But we were very excited when we got the structure. Also, like crystallography, that's the only thing that really gives you that, like, oh, there it is. I'm gonna yell now. Oh, I love crystal structures. Okay, so there is the starter solvent in those pores, but we were able to show that you could basically move the solvent through. And so we can move the solvent, the single crystals were staying intact. We would recollect the data after changing out the solvent, then dissolve them, show by NMR that the solvent was changed, structure was intact. And so these systems were by definition porous. And so this was the first ever example of any of these signal hole bonding interactions exhibiting porosity, and crystallography was critical to this. And so we were really excited about it. The cloth was taken, so we're stuck with chaff, but so it goes. These systems were porous. They were not permanently porous. So if we think about a metal organic framework, what do we use it for? A lot of times it's gas absorption. You can pull everything out of the pores and it retains a structure. If you take everything out of the pores of this, it'll collapse. And so what we've been, this is a few years ago now, is that the journey that we've been going on is getting tellurium, because very clearly is that when you go from selenium to tellurium, you're going to make that structure much more robust. And so we published a paper last year where we were making these hybrid systems. And again, this is just because of the synthetic challenges of using tellurium. But in this case, we were going from systems with selenium where we're getting these huge fat single crystals, massive single crystals. And every time we introduce more and more tellurium, we're getting smaller and smaller crystallites. And at the time, we weren't really aware of what micro-ED was bringing to the table. And so, we published a paper that was single crystal and PXRD. We didn't use micro-ED, and that was our own fault, really. Because, the powder looks nice, but we don't have those atomic level structures. But all of that journey led us to finally figuring out how to do the synthesis. We had to isolate this super hot electron-rich tryptosine system. Just had to be really rigorously air-free chemistry, and then we were able to make this TRIP3 test. And so this is where microED comes into the picture, is that when you make this molecule, it wants to assemble so badly that in the reaction mixture, it starts raining crystals. It immediately assembles as it's formed. But we're not controlling that, and so those crystals are really, really small. And so at first, we did what, if you don't want to drive Chris mad, you do get your PXRD, make sure that your samples are actually nice and crystalline. And then we could see that these did align with the honeycomb type lattice for all of our different systems. And then really incredibly, and this was done by Pierre down in Houston, is that we were able to see through microED is that we did have that honeycomb type system. And I can't really emphasize enough how small these tiny little crystallites are. This really blows my mind that we were able to get this structure. And what was super important here, right, is that these are collected under ultra high vac. This structure is stable under ultra high vac, which tells us that it's permanently porous. And so here's that gas absorption isotherm, 77 K nitrogen, that clearly shows that this system is permanently porous. And so by using the microED, we are able to then correlate that structure to our permanent porosity. We've been able to do some fun things. We can actually regenerate these materials. We can heal these materials, which is super fun, something you can't really do with them off. And then the final thing I'll say really quick is that because we had these atomic level structures, we could then take that structure and do a lot of calculations on these systems, knowing what that structure was. And so one of those things that we figured out from first an abbreviated calculation is that we're getting 1D band dispersion through those non-covalent interactions, which is a very weird thing. And we can actually show now with those full structures, comparing a hydrogen bonding system to a selenium-based system to a tellurium-based system, that these interactions are leading to semiconducting behavior that we're extremely excited about. So I'll leave it there with saying that what we think we've been able to do, validated through single crystal, powder, and microED, is basically establishing an entire new class of permanently porous materials through these interactions. And so I want to thank again Rigaku and Northwestern for the invitation. Here's my wonderful group. This is the park by my house. Right about here is me saying, no, the rain's going the other direction. And then about 10 minutes later, everyone's under the tent and I'm getting rained on in shame. And then thank you to all of our sources of funding, incredible collaborators. These people have been absolutely critical to our work. And thank you for your time. I'd be happy to take any questions.
Thanks for your talk. So with so in the structures you showed here, you had basically the donor, the nitrogens, and the acceptor, the tellurium, like right next to each other. Have you thought about like separating the two and how that would affect the electronics of it? Would it make the bonding between like a donor and acceptor that's spaced out in the molecule weaker or stronger? Could you introduce more types of directionality, different structures with that?
Yeah, so I'll just it's annoying nomenclature. The tellurium is the donor, the nitrogen is the acceptor.
Oh, sure.
Yeah. It's like hydrogen bonding. It's really weird.
Right.
So we have with our chalcogen bonding work, we've been still pretty stuck on these chalcogen and diazo groups because they behave super well. We have a whole other platform on halogen bonding. And in that case, we've done a lot of different work looking at different heterocycles, different spacing, different compositions, all these things. And so for that, we do a lot of just very simple DFT using ESP maps as a kind of a first principles prediction of electrostatic interaction. So these chalcogen and diazols were well-established heterocycles in the organic semiconductor community. And so they just, it turns out the organic semiconductor community was kind of accidentally doing this and not knowing what they were doing. And so it worked out for us. But we haven't really played with these derivatives yet because there's just so much information still out there that we're pursuing. But yeah, good question.
Obviously a great talk, but the selenium complex, you said that it has a salt within it. Have you tried freezing the crystals and then evacuating it? Because it'd be interesting to see if on the micro ED you could put it at 100K and then even under that vacuum maybe pull that solvent out, or is that solvent those trichlorobenzene?
In that structure, that was the trichlorobenzene. So yeah,
So that's the only thing you can put in there so far.
in that system, yeah, we could exchange all three of the chloroaromatic solvents for each other. This was, I mean, like I said, this works from a handful of years ago. We've moved on to the tellurium-based systems, and you just see a dramatic increase in the robustness of the system. This system was limited, is that if you tried to exchange the chloroaromatic solvents for, let's say, pentane, then it would demorphize or relax into a denser structure.
Okay, I just was curious because I was just wondering whether in a micro ED would solve a problem of getting one without solvent in it.
Yeah, potentially.
If you had a solvent that you could put in there, that it would come out on the vacuum.
That's an interesting question to try basically a alternative approach. Because like when we were doing this, we were extremely focused on getting as big a fat a single crystal as possible, right? So I mean, you can see the year here. And so we hadn't really worked the other direction at all. So yeah, it's an interesting point.
Do you think that you could change the parameters of the tellurium compound to get you a bigger crystal?
Yeah, so one of the things that we've talked about is basically when we do the reaction, is that having a competitor in the solution already. So instead of having the threefold symmetry of what we call trip-free TES, having like just like benzotellurodiazole in there, so just one unit of that already in solution. So that when you make it, there's a competitor in there. So like if people are getting familiar with Milligran frameworks, is that if you want to grow fat crystals of MOFs, is that you'll put like trifluoroacetic acid or acetic acid in solution to compete with the coordination. So we're thinking about basically a competitor modulator technique in order to grow larger crystals, if that is something that we need to do or want to do. Yeah.
You mentioned at the end that you were showing semiconductor properties. Do you have a sense of where the electrons are flowing?
Yeah. I don't have the beautiful pictures, but so basically this is just one of the dimers, but it continues. It's a edge-on interaction, basically the tellurium p orbital with a pi orbital on the other side, and so it's actually an extremely weird, unique type of semiconductor behavior. This is not how they behave normally, and what we're super excited about is because I don't have that slide here. Hydrogen bonds are nodes. Hydrogen bonds will basically always create an electronic node, and so we've launched a whole other platform in our lab now on this behavior. So what these interactions give you is an ability to predictably assemble molecules into materials and imbue electronic behavior that you won't see with a hydrogen bond. So we're extremely excited about it. Yeah. Yeah. So you can see that the valence band and the conduction band. If you can see the colors, you can see that you have the contributions from those atoms. Yeah. Yeah. Okay.
I'm curious if you investigated playing with the aromaticity of the trypsin core, either through like phenyl, substituent functionalization to kind of try and modulate this like crystal growth interactions. Like you obviously got into the very robust tellurium, like away from the hard to assemble selenium, but curious if you're interested in like trying to get somewhere in the middle.
Yeah, so that's a really good question. So basically, can we tune the electronics through the organic core as opposed to just replacing the chalcogen? It's definitely something that we've thought about, right? We do have to be concerned about this packing here. If we want to retain this structure, we don't have to. This is just, we chose the honeycomb because when people see the honeycomb, it just like aesthetically lands. We're making a lot of two-dimensional systems now. Because of the semiconducting behavior that we're seeing, we're making planar flat 2D systems to actually get delivered, basically like chalcogen bonded graphene is what we're going after, which we're really excited about. We really think that we've just absolutely opened like Pandora's box. There's so many possibilities, and I have a 12-person group. I'm not at Northwestern. I don't get an 80-person group, Chad and Omar. Yeah. But yeah, so there are a lot of possibilities, and tuning kind of to multiple questions here, tuning the electronics of those interactions is something that we are interested in. One thing you have to be aware of is that, you know, if you modulate, like, say you fluorinate that, that's not just going to affect the chalcogen, it's also going to affect the lone pair on the nitrogen as well. So there's kind of a push-pull.
Exactly.
Yeah, yeah.
Thanks.